Let's just jump right into it. Welcome to The Explainer. Today, we're diving headfirst into a literal mathematical detective story. We're going to explore a 2026 paper by Kyle McLean Smith, and let me tell you, it bridges abstract geometry, historical alchemy, and physical hardware in a way that is just completely mind-bending. It's a journey that really challenges how we name, understand, and actually physically build the mathematical models of our world. Think about this for a second, just to get our curiosity going. What actually happens when a flawless mathematical sequence, one that perfectly mirrors real-world metals, suddenly just hits a wall with a bizarre, unexplained anomaly? Imagine uncovering this perfect blueprint of the physical universe, only to find one single coordinate that just doesn't seem to fit reality. That is exactly the puzzle we're unpacking today.
All right, part one, the continuous B spectrum.
So the paper lays out this brilliantly simple three-step process to generate what are known as the metallic means. First, we take a continuous right triangle spectrum and apply an A=1 data normalization. Now that's really just a mathematical way of saying we level the playing field. It lets us compare wildly different variables on a single dimensionless axis. Step 2 is where the absolute magic happens. We set the continuous parameter b equal to m divided by 2, where m is an integer. And then step 3, boom, this perfectly elegant formula generates the entire family of metallic means consecutively without skipping a single beat. It essentially proves that this isn't just random math. It's a tight, continuous geometric spectrum.
Moving right along to part two, generating the metallic means.
Just look at what happens when you actually run the numbers. By increasing our integer m from 1 to 6 and setting b to m over 2, the math produces this stunning series of ratios. When m is 1, you get approximately 1.6180, which you probably know as the famous golden ratio. Make m equal 2, you get the silver ratio. M equals 3 is the bronze ratio. So these consecutive integers perfectly map to specific, tangible metals. It's an incredibly perfect metallurgical taxonomy, right? But notice what happens right in the middle there. After bronze, something weird occurs. We hit this placeholder called subtle, and then we suddenly jump right back to real, tangible metals, with copper at m=5 and nickel at m=6.
Yeah, so the glaring question is this anomaly right here, the number 4. Why on earth does this hyper-precise mathematical precision suddenly devolve into a vague, poetic term like subtle, right before picking back up with actual copper and nickel? Why doesn't that fourth integer map directly to a tangible metal like everything else in the sequence?
Which brings us to part 3, the subtle mean misnomer. Okay, let's rewind a bit. Back in 1999, mathematician Vera de Spinel was mapping this sequence out, and she literally just ran out of standard metal names after gold, silver, and bronze. So she just slaps the label subtle mean onto m=4. It was purely an abstract poetic label used for quasi-periodic tilings, but, and this is crucial, the 2026 paper completely calls this out and issues a massive correction. It argues strongly that from a physical and circuitry standpoint, m=4 isn't some abstract aesthetic space at all. It is, in fact, the true, unyielding physical node for metallurgical copper. The paper is essentially saying we have to swap out this poetic label for the rigid reality of actual hardware circuitry.
Part 4, Newton's alchemy and copper.
Now, you obviously know Isaac Newton for his laws of motion, right? But the guy was also deeply, deeply obsessed with alchemy. The paper highlights a fascinating detail. Newton spent years studying this remarkably unique purple antimony copper crystalline alloy. He actually called it the net because it formed a highly regular, perfect geometric grid. Newton firmly believed metallic growth wasn't random at all, but rather followed strict proportional geometric laws. And honestly, his intense obsession with this exact copper grid gives us a massive historical clue. It points us straight at copper as a rigid geometric coordinate, perfectly echoing the math we just saw in the metallic means. It is just wild to look at the timeline of all this. You've got this centuries-long thread connecting some seemingly disparate ideas. We literally start all the way back in the 1300s with medieval philosophy. Then we jump to the 1700s with Newtonian alchemy and his copper net alloy. Fast forward to 1999, where Spinel gives us the mathematically accurate but kind of poetically misnamed subtle mean. And finally, we arrive at this 2026 paper, which ties the whole shebang together, correcting m=4 to metallurgical copper so it aligns with modern quantum geometry and hardware design. And that leads us to part 5, the doctrine of Heaksity. So to lock this whole unified theory into place, we actually have to go back to that 14th century philosopher John Duns Scotus, famously known as the Doctor Subtilis. He defined a doctrine called haesiality, which literally translates to thisness. Think of it as the ultimate grounding mechanism. It is the specific quality that takes an abstract concept just floating around in theoretical space and drops it into exact physical reality like a heavy anchor. By applying this medieval doctrine of thisness, the paper strips away Spinedjal's poetic placeholders. It forces the mathematics to stop floating in the ether and absolutely anchor itself to a tangible physical state. And here is the real payoff of applying that thisness. These facts firmly establish exactly why m equals 4 isn't just a subtle mean floating around out there. When you truly analyze the mathematical node of m equals 4, it matches real-world elemental valence perfectly. It aligns beautifully with actual physical electron shell configurations. It corresponds identically to real-world electrical conductivity. By applying the doctrine of thisness, the author formally corrects this node to metallurgical copper. It transforms a nice aesthetic label into an exact, unyielding, and, as the paper brilliantly calls it, unrug-pullable physical hardware coordinate. It proves that the math is the physical hardware.
So, as we wrap up this explainer, I want to leave you pondering this final, profound question. We've seen how a continuous mathematical parameter directly generates the exact coordinates for real-world metals, totally bypassing abstract labels to find a true physical home in metallurgical copper and circuit design. It begs the question, if our theoretical equations perfectly predict the physical constraints and structures of the universe, literally right down to their electron shells, are we actually inventing math, or are we simply discovering the underlying blueprint of physical reality? It's an absolutely incredible shift in perspective. Thank you so much for joining me on this explainer, and I really hope this sparks your curiosity to look at the geometry of our physical world in a whole new way.